the configuration here has changed all of a sudden. So you have to readapt to the new environment here. So today is the fourth lecture in our series of pre-laboratory lectures on, is it the fourth one? It's the fifth one. So today we're going to talk about plotting data, graphing data, how do we present our results, because if we do some good experiment, we show a lot of experimental skill, we are meticulous in observation, in logging our laboratory activity, but if we are not able to present it in an effective and efficacious manner, then it's really of no use. So today I'm going to tell you some of the tricks of the trade. Now when you stop talking, I'll start the lecture. Can you please settle down quickly? No need to find friends. Please find the seat that's first available. और अगर पिछली रो में बातें हुई ना, I'm going to stop this class. All right. So now this is a distillation of what we've been doing in the physics laboratory for the past 7 to 8 years. You will not find this material in any book whatsoever. So these are the tricks of the trade, the tools of the trade that are used in accurately, concisely, precisely, and clearly presenting scientific data to your peers, to your teachers, to the scientific community at large. So it's good if you all pay attention. Now, I would recourse, or I would talk a lot about a paper that was published in the year 1917, and this was work done by an American physicist, Robert Anderson Millikan. Millikan, as you might know, was one of the physicists, he won the Nobel Prize by the way, who actually found out the charge to mass ratio of an electron through a famous Millikan's oil drop experiment. But he was also the scientist who actually determined the value of Planck's constant using Einstein's theory of the photoelectric effect. So as you would know, Einstein won the Nobel Prize for his description of the photoelectric effect, and Millikan was the first experimenter who actually performed an experiment and showed that the experiment corroborated Einstein's theory. And using his experimental data, he was able to find out the value of Planck's constant, one of the fundamental constants that we know. And this is a picture or a schematic diagram made by Millikan himself that is published in the paper from 1917, which went into Physical Review. Physical Review is a flagship journal of physics. So we're talking about what happened 98 years ago. And we're going to use this data over and over again to show how data can be scientifically represented, albeit graphically. Now what this basic experiment looks like, you're all familiar with the photoelectric effect. Light falls onto a concave shaped cup that is made of a certain metal, say sodium. Electrons are ejected, so they are ejected by the photoelectric effect, they move towards Q and they constitute a current through this circuit. And a voltage can be applied between the electrodes P and Q. And this voltage could be such that Q is at a negative potential, which means that it will make the electrons difficult to reach Q and the current will diminish. So B can be a blocking voltage. It can make the life of electrons really difficult so that the photocurrent decreases. And by looking at the potential, the negative potential at which the current ceases, one can determine the work function of this metal. So this is something that you're already familiar with, and this is the mathematical description. The energy of the electrons that are ejected from electrode P is half mv squared, and this equals Now the maximum value of the potential of the kinetic energy an electron gains equals the potential difference between P and Q multiplied by the charge on an electron. But photons are bringing in energy, and each photon brings in an energy hf. But W of that energy is used in overcoming the work function because the electron has to come out of the metal. So the remainder energy that the electron has after it has been ejected from the surface is hf minus W. So, and V naught is applied potential. So if we rearrange this equation a little bit, this is what we would get. And if we make a plot between the frequency of the incoming photon, which really tells us about the color of the photon, of the incident light, and the applied potential, it will be a straight line. Now, E is the charge on an electron, and Millikan had already found out the charge to mass ratio of an electron, so the charge on an electron was known. This is a picture of Millikan's oil drop experiment, a different experiment, which was used to measure the charge on an electron. So by looking at the slope of a graph, one could in principle determine the value of the Planck's constant. And by looking at the intercept of the graph, one could in principle determine the work function. And this, by the way, is a photograph of Millikan's apparatus. Now, if you look at Millikan's paper, it has a huge plethora of long, tedious tables, careful observations. This is the volts that are applied. This is the deflection of the galvanometer that was measuring the current. This experiment was performed at 5,461 angstrom, which is 546 nanometers, which is yellow-green light. This experiment was performed in the reddish region, 434 nanometers, and so on. This experiment was performed at 253 nanometers with ultraviolet light. So in each case, he has a table of volts, the applied potential, and the deflection of an ammeter, which is measuring the photocurrent. So there are a large number of tables in this paper. But if you just look at the tables, nothing emerges from this. It's very hard to decipher or understand or comprehend what this experiment entails. So the tables look really nice, but in order to interpret what's going on in the experiment, something more is needed. Therefore, Millikan made the right choice. He drew a lot of graphs in his paper, and if you observe here, these graphs are all drawn by hand on a graph paper. So here is the axis, the voltage axis, and on the vertical scale, one has the photocurrent, which is the deflection on the ammeter. And if you observe, at a certain critical point, if the voltage is below this point for a certain frequency of light, there is no photocurrent. This critical point changes if the frequency of light changes. So this is in exact accordance with the description of the photoelectric effect. You need a minimum frequency of light to eject electrons from the surface of the metal. Alright? It's not possible that you keep on shining light of a low frequency on a metal and eventually the electrons will gain enough energy to be ejected from the electron. The frequency has to be above a certain critical threshold. So only above a critical threshold does photocurrent emerge. So Millikan drew a lot of these graphs. By the way, if you don't understand the entire details of the physics, it doesn't matter. I'm just trying to convey a message here. The power of the language of graphs, pictures, plots. Here's another graph. And this is the model that's proposed by Einstein. So what Millikan really did now was he plotted the voltage on the vertical axis and the frequency of the incoming light on the horizontal axis. And he observed a straight line. But what did he really observe? He took these data points. If you observe carefully enough, there are data points here, small circles here. These are experimental data points that Millikan observed. No experiment can give you a continuous line. It can only give you points, data points, experimental data points. Because you cannot negotiate this entire line. You need infinite amount of time to do that. It's just like the Zeno's paradox. If you would like to move from point A to point B and you would like to do it continuously, you would actually have to negotiate all the distances between the two extremities of this table, but that's not possible. So what an experiment really does, it gives you finite or discrete data. It gives you sample points from a large set. And this is what Millikan did. He observed, he made a measurement at this frequency, at this frequency, at this frequency, and so on. Because the light sources that were available were discrete, they were finite, they were countable. So he used all the light sources that were available to him and made measurements at those frequencies. So he then drew these points, and then he drew some kind of line that fit between these points, that negotiates or talks to these points. Now this graph models this equation quite well. If one finds the slope of this graph, I hope everyone knows what the slope of a graph is, then theoretically speaking, if this model were to be correct, that slope must be equal to h over E. Now E was determined, the charge electron was determined from a different experiment by Millikan himself in 1909, 8 years before he performed this experiment. So he knew the charge on an electron. So if he calculated the slope, he was able to, in principle, to determine the Planck's constant. And by looking at the intercept, where this graph intercepted the axis which corresponds to frequency equals 0, one could in principle determine the work function of this material as well. So from this melange of data that was put in the form of a table, which was really nicely done, but it was difficult to comprehend or pick up some message from this table, everything became smoother as soon as he drew a graph. So this graph opened up a new vistas of enlightenment upon Millikan and all the readers of this paper. So it's a graph or a plot of data that actually opens up new possibilities in physics. So in most of the experiments that you perform, you also have to draw graphs or plot data. And each experiment, each kind of graph that you draw will have a different kind of meaning. And we'll expect you to interpret the data, that graph, in a different way. Every experiment is different. There's no one rule that fits all. So we've designed an experiment so that each experiment gives you a different way of interpreting graphs. Alright, we've already seen this slide in one of our earlier lectures. If you have data, then you need a model to fit that data. But if different models are available, for example, you have a model of a straight line, a Bigley model, you'll have to choose one of these models, even though all of them seem to apparently fit the data. So which model do we choose? We need to have a strong theoretical understanding of the underlying principle to pick up one model against the other. Now, generally, in physics, there are different kinds of models, but the models that we will frequently encounter are the ones that I'm going to show here. So what is a model? A model is just a function. You have a variable x and you have another function y of x. Now when I draw models, यार आप बातें क्यों कर रहे हैं? आपको किस बात का मजा आ रहा है? देखिए, I am trying my best to compress everything in 50 minutes, and I'm trying my best to give you a good overview of what this huge field is. So please pay attention. No one's going to help you in the laboratory the way I'm helping you at this moment, because then you'll be mostly on your own. Now, whenever I draw models or theoretical fits which do not correspond to experimental data, remember I'm drawing solid lines, continuous lines. In this example, there were two kinds of data. One were these discrete points. These discrete points were from experiments. So the points represent experimental data, whereas solid lines, continuous lines represent theories or models or fits. So here I'm going to show you different kinds of models. We have a linear model. This is a graph of y equals x. This is the x-axis, the y-axis. A graph of y equals minus 3x. You should know what is meant by the slope of a graph. These are straight lines, the slope is quite easy to understand. The vertical displacement divided by the horizontal displacement. This again is linear, but it has a certain intercept as well. So this is the point where the graph intercepts the x equals 0 axis. Again, this is another graph. Alright? The only difference, so both of these graphs represent the same model. 3x minus 6.7, 3x minus 6.7. The only difference between these graphs is that I've chosen different scales for the y-axis. Here the y-axis goes from minus 10 to plus 25, here it goes from 0 to 30. So the scales may change, the shape of the graph remains the same. So you also have to look at what the axes are. What are the starting point and the final points of the axis? What's the range of the axis? So both of these represent the same linear models. And notice something very interesting here. Okay, little reveal. When I write 3.0 minus 6.7, I'm being very careful. I'm acting like a mathematician or a purist here. Because what I'm doing here, I could have easily written 3x minus 6.7. But I'm respecting that this intercept is given to two significant figures. One decimal place after the decimal, one position after the decimal. So I would like to write some digit after the decimal. So I'm acting like a purist. I'm being very proper here, being very formal here. 3.0x minus 6.7. I could have even written 3x minus 6.7. That's alright, but it looks a bit sloppy, a bit clumsy. So all of these are minute details which the hawkish eye would actually pinpoint. And if you're a reviewer of a journal article, of some journal, you would actually fall upon these points quite avidly. Now there could be quadratic plots as well. Y equals x squared, y equals z squared. So this is what quadratic curves look like. For example, if I have 3x squared minus 10, if I plot 3x squared minus 10 versus x, this is what the plot looks like. Now, if you notice here, the minimum point of this graph just touches the x-axis. But if I were an intelligent experimenter, what I would do, I would extend the y-axis a little bit so that I can see where this minimum point actually lies, so that it doesn't touch this axis. So, because I would like to find out where the minimum point is. So these are minor details you can adjust in the final plots that you make. I don't want my minimum point to intersect one of the axis. So I just extend the y-axis a little bit so that the minimum point lies a little above this horizontal base. So these are minute points that you will learn by experience. Alright, now you're all familiar with what happens to a mass that is attached to a spring. Now, if mg is the weight of this object and it obeys Hooke's law, you have mg minus kx where x is the extension. So ignore beta for a minute. If I plot a graph between on this axis, if I have the weight or x, or if I have the weight, and here I have the extension, or I can even have the extension here and the weight here, I will get a straight line. But if I introduce some non-linearity, some beta becomes non-zero, I will obtain a graph that looks like this, or a graph that looks like this. Now here the non-linearity is much smaller than the non-linearity here. This is a smaller non-linearity, but by the look of it, it looks like a much non-linear curve. The reason is the y-axis. The y-axis here extends from minus 5 to 40. Here it extends from minus 100 to 500. So this is a much stronger non-linearity. So you really have to be careful about what the ranges of the different axes are. Alright? So you need to have a good conceptual understanding of the axes. What are the ranges of the different variables that you're encountering in the experiment? So you have a linear curve, you add a tiny little bit of nonlinearity, the shape of the curve can change drastically. Now it's also quite common to superimpose different graphs on the same base. For example, if I were to include the previous example and I would like to put all three graphs on the same plot, this is what it would look like. And this superimposition of graphs on the same base can actually highlight the difference between the graphs because all of them are referring now to the same vertical axis and the horizontal axis. So you can really compare different theoretical models by putting everything on the same graph. So it's quite a common practice of superimposing different graphs on the same plot so that you can make easy comparisons. So here it's quite obvious that the red line shows the greatest nonlinearity. And of course it does, because beta has 0.5. Green has an intermediate beta. And y equals minus x is just linear. Now on this scale, this looks like a flat line. But it's not really flat. From the previous example, we know it's not flat. However, changing the axis may change the visual perception of your data. So it's important to keep in mind what would you like to highlight. If you would like to highlight the role of nonlinearity, you would like to put all three graphs on the same plot. If you would like to show that this is linear, then this is not a good graph, this is a better graph. So it all depends upon what you would like to show your readers. Now, another point of consideration is that sometimes we really have to care about these things, is that this is a red, green and a blue curve. But if you don't have a color printer, generally we make prints of all plots and put them on our notebooks. It's important to have a printed record of your laboratory activity. If you don't have a color printer, all three of these lines will look just the same. So what you would like to do in practice, you would actually like to use different kinds of lines for these three graphs. So even if you don't have a color printer, you have a black and white printer, you can actually tell the difference between these graphs. And these points are really important when you publish your work. Because if you would like to publish your graphs in color, it costs you much higher. So you do not want to publish in color, you would like to publish in black and white. So it's really important to keep these points into consideration. No book will actually tell these points to you. I haven't seen a book so far which does that. Now there are other kinds of models. There are exponentials. So I'm just serving all the different kinds of models and theories that you will encounter in this course. You will have a decaying exponential, an exponential that goes down. This is y equals 5 e raised to minus x. Here is the y-axis, here is the x-axis. So it decays with a certain time constant. Here is a 5 sine squared 2x graph. Here is a graph of a sinusoidal function that decays with time. So if you have an oscillator like a pendulum, ideally it should have a sine 2x curve, but it eventually decays with time because the oscillation is damped. So this is what the graph will look like, and some of the students will perform an experiment in which they will see a graph of this kind. Now if you compare these two graphs, here the only difference is that in the power of the exponent we have e raised to minus x over 5. Here we have minus x over 50. The only difference between these graphs is that the decay is much weaker here, is much softer or gentler here. Here we have 50 under the x. So it takes about 50 units on the x-axis for this graph to decay to 37% of its original value. So the decay here is much smaller. So this, what you find in the denominator on the exponent tells you the rate of decay. So both of these are decaying graphs, but the time constants are different. One is a gentler decay, the other is a far steeper decay. And you will actually come across experiments in your lab in which there are different decay constants. Alright, now both of these graphs I claim are depictions of this function y equals 5 into e raised to minus x, although they look vividly different. But both of them represent the same function, the same mathematical expression. And how do we know that? If we take the natural log of both sides, this is what we get. Now if we plot the natural log of y with respect to x, we expect to see a straight line whose slope is minus 1. Here there is a coefficient minus 1 and the intercept is natural log 5, which is about 1.6. So this is called linearization of data. There are a huge variety of experiments in which the data is non-linear, but you would like to convert it into a linear form because it's easy to find out the slope and the intercept. The slope and the intercept can carry some valuable information, as you would know. So this process is something that you should be really comfortable with. It's called the linearization of data, and this is an example of a semi-log plot. One of the axes is on a logarithmic scale, the other is just the linear scale. This is a semi-log plot. Okay, so you can linearize data by taking the logarithm of both sides. Remember, I'm not drawing experimental points here, these are just theoretical models. That's why I'm showing them by solid continuous curves. Any questions to this, up to this point? I can take one question. Sorry? Linearization. किसी चीज को linearize कर देना, linear बना देना, straight line में convert कर देना. Now let's move back to Millikan's original experiment. So I took one data from his 1917 paper and I just reproduced the results that Millikan produced in the form of a table. Here is the stopping voltage, here is a wavelength in angstroms. I convert this wavelength into frequency by this formula. So if you notice here at the top of the table I have into 10 to the power 14 per second or hertz. So each one of these values is being multiplied by 10 to the power 14. I don't want to write 10 to the power 14 over and over again. So I just put it once in the header of the column. Here I put angstroms. So I don't want to put an angstrom here, 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 here. So I just put the common multiple in the header of the column. So I made a table. This is the starting point for any graph. You make a table. You make a nice tabular representation of your data. Alright. Now I would like to show you different ways of plotting the data. Now if I were to take the frequency on one axis and the stopping voltage on the other axis, this is the graph that I would get. But let me warn you that this is an incorrect result. This is an incorrect graph. This graph is not acceptable. Because what this graph is actually showing is there is some kind of non-linear relationship. Look, it's not straight line. It's some non-linear rugged line, zigzag kind of line, which is not representative of the data itself. Because the data is only sampled at discrete points. So this is not a correct representation of the data. This, however, is a slightly more acceptable version of the data, because now what we've done is we put data points which correspond to the experimental values onto the graph. And these data points are represented by these circles. These are called markers. So I put markers for the experimental data points and I've connected each point through a straight line. So this is a straight line here, a straight line here, straight line here, and the straight line is still zigzag because it's connecting two consecutive points. Still, it's barely acceptable, because what this graph would actually tell you that if you have a frequency between 6 and 7, say 6.5 into 10 to the power 14 hertz, this would be your data point, but that's not correct. You've only sampled these discrete data points, and any zigzag line between the data points is just synthetic. It does not mean anything. Alright? Another thing you will observe while I'm drawing these graphs, I've drawn all of these graphs in MATLAB, the software that you're going to be using, is that I have put all of these tick marks, these tick labels, 0.5, 0.00, 0.05, to the same number of significant figures. So here I could have easily written 0. But I've written, I'm a purist, I would like to be proper, I'm careful, I love my data, so I would like to put in a 0.0 here as well, so that all the digits are quoted in the same number of significant figures. So this is something to be really careful about. So this graph is barely acceptable. By the way, in this graph I have also put in a grid at feedback. A grid is optional, but it looks nice sometimes. Now this is a better representation. This is a more faithful representation of the experiment Millikan performed. It just gives you the bare points that Millikan measured, without any over-interpretation, without any artificial line that connects these two points. This is a much better representation. In fact, now the point is that this experimental data has to be fit to some theory. Now that theory will give you a solid line, which is generally a straight line without any zigzag. So what one would do is draw a line that goes between these points. Now there are different ways of drawing lines. Which line would I draw? I will have to make a choice. I will have to make a choice amongst the different lines that I can draw. Okay, I have to make a best fit to the data. And there are different ways of doing that. And we learn how to choose one particular line that best fits the data. So fitting means that you have a set of experimental data. These are just discrete markers. Now you would like to draw a solid line that fits the data. That is a close approximation to the data. Okay, this is called a best fit line. There are different kinds of best fit lines, and we learn about particularly one of them, which is called the least squares best fit. Alright. Now, with the help of this data, Millikan was able to find out the value of the Planck's constant. So he drew the best fit line, which we'll learn about later. This best fit line represents this theoretical model. The slope of this line was calculated as 3.96 into 10 to the minus 15 volts second with the proper units. This intercept was calculated as 4.25 volts, and from this slope, the slope of this best fit line was able to calculate Planck's constant. Now this was the second determination of Planck's constant. The first determination was done by no, it was Max Planck's theory, but the experiments were performed by Langevin and Prussian. So there were two scientists who fit data from a black body to find out the value of Planck's constant. This was the second experimental determination of the Planck's constant, and it's pretty close to our currently accepted value. And the wave function is about, the wave work function is about 4.25 electron volt, which seems like a good value for group 1 elements such as sodium. So from the graph, you were able to calculate the slope and the intercept, and from the slope and the intercept, you were able to calculate physical quantities or estimate physical quantities. If you just had bare tables, like skeletons, without any flesh on top of them, you wouldn't be able to calculate these physically meaningful quantities. So you need to plot data and plot it properly. You need to graph data and graph it accurately. Just tables will not do, because you will miss the patterns. We are visual beings. Our evolution has been such that over 150,000 years, we look at visual imagery. We are scientists, but we are humans after all. So we take a peel from images, from graphs, from sketches. And it's sketches and graphs that give us physical meaning, insight into the physical process. So it's very important that you understand the value of proper plotting and graphing. Alright, now there are four ways of drawing graphs. For example, in this graph, it just has the same data points, but there are two problems with this graph. First is that I'm excessively putting excessive labels on the y-axis, even though the resolution of my experiment is not fine enough. So all of these values that I'm putting really don't make sense, because either my measuring instrument does not have a fine enough resolution, or I don't have time to perform measurements at such a fine scale. So I'm putting excessive points on the y-axis. Look, here I have 1, 2, 3, 4, 5, 6 points, and I have so many tick labels, it doesn't really make sense. Second, I have put in too many lines in the grid. So as my visual perception would actually stumble upon the grid itself rather than the experimental data. I want to keep my graphs as simple as possible so that I'm directly appealed by the experimental data and the best fits and the axis, and not by flowery embellishments, by some excessive scale or by some excessive grid or some pretty patterns that one sees in the background or some watermark on the graph. I don't want to see any of this. I want to have direct access to the data. Now here's another choice of a poor graph. My data points are clustered between, say, 5 and 12 into 10 to the 14 hertz. But I've drawn my graph all the way from 0 to 6, because generally speaking, we would like to start our graphs from the origin. But this doesn't really make sense, because half of the area inside this graph is just devoid of experimental points. There are no experimental points in this region. So I don't really want to make this region. It's over excessive. So I have to choose the range of my axes properly. Okay, so that I remain faithful. I show high fidelity to the experiment that I have performed. I do not overinterpret or underinterpret. I do not make egregious claims that are exaggerated. I want to stick to what I've done. I do not want to show off. I just want to perform an experiment and draw a graph that faithfully represents my data. ठीक है, कोई सवाल? कोई सवाल? कोई comment? All right. Now here's another example. So what I've done here, one thing that I've done a little bit clumsily here is that I have put in a 0 here. I should have really put in a 0.0. I should have put in a 1.0, a 2.0 here. But sometimes you can get away with this level of clumsiness. But one thing that I've done which appears untidy is that instead of clumping the 10 to the power 14 factor with this axis label, I've just put in a 10 to the power 14 at all the points. Now this is correct by all means, but it doesn't look nice. I'm overly cluttering my graph. So it's good to put in common multiples, lump them together in the axis label, so that I don't overly repeat them. Now some examples of linearized graphs. I have an object here, a cylinder. This is one experiment that students will perform, and it's heated up to say 200 or 300 degrees centigrade, and then you attach a thermometer or thermocouple to it and you see how the temperature drops with time. So this is the experimental data, and you turn on a fan in another part of the experiment so that convection is forced, the cooling is much rapid here. So this red curve represents natural convection, cooling by itself, and the green curve represents when we force convection, when we turn on a draught of air, for example. Now these are exponential decays, and if I would like to find out the rate of decay, I would like to linearize this graph. So I take all of these data points and find the logarithm of these data points, and what I get are straight lines after linearization. And then it's possible to find the slope of these lines. So if this is my decay rate, it's exponential, I take the natural log of both sides, this turns out into an equation of a straight line with a slope 1 over b, and this b is the decay rate, the rate of convective heat transfer, the rate at which this object is losing heat to its surroundings. Alright, so I can linearize graphs. It's very commonplace to linearize exponential graphs because they are easy to fit, and it's always nice to work with linear data. Another more complicated example, if you have a light bulb. Now the light bulb is a household appliance. There are probably tens of millions of light bulbs in Pakistan. Now, but the physics is really cool. If you look at the power that goes into the filament of a light bulb, all of the power goes into radiated heat. That's what you really want. You want your bulb to be really luminous. So you would like all the electric power to go into heat. So this is the Stefan-Boltzmann law, which tells you the amount of heat radiated. It's a constant times the area of the filament and the fourth power of the temperature. Now when the temperature of the filament changes, its resistance also changes. Anything that a resistor that gets hot, its resistance goes up. This is what happens for a resistor. Hot resistors show more resistance to electricity. You cool down a resistance, the resistance drops. So a model is that if you increase the resistance, the temperature goes up, but there's a power here, some index, some exponent gamma, which is unknown. We propose a model which is a relationship between the resistance and the temperature, and say that T equals R raised per gamma. Now we place this fourth power into the above expression, and we obtain this relationship. The electric power equals some constant into resistance times resistance exponentiated to 4 gamma. Now if I plot R versus P, it's going to be an exponentially rising curve because it's a power law here. So what I would like to do, I would like to take the logarithm of both sides. So I take the log of P, I take the log of the right hand side, I get log of C plus 4 gamma log of R. Now if I would like to linearize this data, I would need to make a plot between two variables. What are the two variables? Will you please tell me, any one of you? Log R versus log P. So what I could do is actually I could put log P on one axis and log R on the other axis, and I will get a straight line. Now when we perform this experiment in the laboratory, these are the experimental data points that we obtain. Remember, all the graphs that I'm showing are data that we've obtained in our own laboratory. Students in the prior years have obtained. Alright? So nothing is out of this world here. Everything is homely and earthly here. All of this data comes from the experiments that you're going to perform. Now, if you make a plot between log P and log R, I get these experimental data points. Okay? Shown by the red markers. And if you look closely enough, there is a small vertical line associated with each marker. That's for the uncertainty of each data point. I'll have more to say about this. But now I have these data points and I can fit these data points to a straight line because the model that I have is a linear model. So I draw a best fit line. How do I draw that? We'll learn about it. But here is the red solid curve represents the best fit line. I can find the slope of that solid curve that will give me the value of 4 gamma. And in this particular case, gamma turns out to be 0.75. So this means that this model that we have proposed for the resistance of a light bulb and its temperature dependence is actually quite a good model. Okay? Quite a nice model. By the way, the temperature of a light bulb, an incandescent light bulb, is half the temperature of the surface of the sun. It's about 2500 kelvins. The temperature of the surface of the sun is 5000 kelvins. So really we can expose ourselves to extreme conditions while living on Earth. Physics is just beautiful if you really come to think of it. Yes? C is some constant, right? It's just the intercept. You don't care about it. This C subsumes the Stefan-Boltzmann constant and the area of the filament, okay? We're not concerned about it, but it's a constant. Now the world of graphs is so rich of different kinds of ideas. For example, in one of these experiments, what you will do is you will have a square wave that is applied to a resistor and a capacitor. And if you look at the voltage across the capacitor and bring it inside the computer, this is what the voltage across the capacitor will look like. There's a rise and a fall, rise and a fall, rise and a fall. In the rise part, the capacitor is charging, so its voltage goes up. And in the fall part, it's decaying, so the voltage goes down. Now this is actually a graph of the experimental data. You bring data into the computer, this is what the computer gives us. Instead of using an oscilloscope, we would like to sample the voltage at about 1 millisecond, after every 1 millisecond. So we take the data into the computer, this is called data acquisition, and this is what the graph looks like. Now I can break this graph into two kinds of regions: charging, discharging, charging, discharging. So I can look at this data and I can just separate out the charging part and separate out the discharging part. So if I just look at the charging part, this is what it looks like. And see what a nice graph I have. My axes are now in milliseconds. So instead of seconds, I choose to put my axis in milliseconds. So I have nice whole numbers, 0, 5, 10. Otherwise, I would have to write 10 into 10 to the minus 3 or 1 into 10 to the minus 4 seconds. So I choose a unit that is close to my point of observation. If you're looking at, for example, nanomaterials, you would not like to choose a unit that goes into meters. You would like to use nanometers as your point of reference. So you choose your units, your base units, something that are closer to the experiment that you're probing. And on the y-axis, we have the voltage. And the data points, the experimental data points, once again, are shown by marks. And the solid line represents a theoretical fit. It's an exponential rising function. So now I have a graph, I break it up piecewise into a rising part and a falling part. And this is the decay part. Okay? So I can have data. Once I have data, I can pick up the data that I want. And this is something that you're going to learn in the computer laboratories that are taking place this week and the next. There are other possibilities. For example, if I have a semiconductor, and if I vary its temperature, its resistance is going to change. So if I vary the temperature from 100 kelvins to 600 Kelvin, its resistance first goes up and then it starts decreasing. So when the resistance is decreasing with the increase in temperature, it's showing semiconducting behavior. Here it's showing some other kind of behavior, some metallic behavior. So I can look at this entire graph and I can show I can observe regions of different kinds of behavior inside this material. This is not possible if you just have a table in front of you. You really need to plot data, graph data, so that you can observe these different regimes of diverse behavior in the same material, in the same system. Alright, now there are other advantages of graphical data. What I have here, this is an experiment that we performed. You have a cup in which you place liquid nitrogen. Now the temperature of liquid nitrogen is 77 Kelvin, which is minus 196 degrees centigrade. Now if you have time on this axis and you're measuring the mass of the cup, which has liquid nitrogen in it, of course the data is going to be coming into a computer, so you're observing mass with time. So with time, the mass is decreasing. This is your experiment. These are your experimental data points. The data points are shown as markers, and then you have a blue line that is a best fit. Now why is the mass decreasing with time? Right? Why is the mass decreasing? My friend, aap bataएं? बताओ. Yellow shirt, huh? आप बताएं. कोई बता दे, आप बताएं. अबू बकर के भाई आप बता दे. Because the boiling point of liquid nitrogen is minus 196 degrees centigrade and it's placed at room temperature, so it's boiling at room temperature. When it's boiling, the liquid nitrogen is vaporizing, so the mass that is registered by the balance is decreasing. So you get a decrease in mass with time. But then you turn on a heater. So you artificially increase the evaporation rate. So when you artificially increase the evaporation rate and then turn off the heater again equilibrium is re-established. If you did not turn on the heater, this graph, this data would have gone down as a straight line. But turning on the heater has actually resulted in excessive decrease in mass. So this line then goes down. So by the excessive decrease in mass, the extra decrease in mass, you find out the heat of vaporization of liquid nitrogen. And this is only possible if you have a graph at your disposal. Now by looking at this graph, you can make miracles, you can do wonders. You can actually find out the latent heat of vaporization of nitrogen. Now this is another example. If I have a solid and I attach a thermometer to the solid and I put this inside liquid nitrogen, this is what the temperature curve is going to look like. Initially, it's at some temperature, it's going to drop, and then I put it inside liquid nitrogen, its temperature is going to suddenly come down to minus 196 degrees centigrade. So the temporal behavior, the time behavior of the temperature of any solid can be observed through a graph. So graphs give us this power to analyze data, to look at patterns, and they provide physical insight. So in the next lecture, we're going to look at the second sequel of this presentation. Thank you very much.